When you spend enough nights staring into the darkness of space, letting the stars settle into patterns that the eye and mind slowly begin to decode, something remarkable happens. You stop seeing random points of light and start seeing structure, rhythm, mathematical choreography. The kind of order that forces you to question whether chaos truly dominates the cosmos or whether hidden frameworks silently guide what we observe, and that realization struck me the moment the earliest tracking solutions for the interstellar object now known as 3I Atlas began appearing on my screen, not in a dramatic flash, not in a cinematic revelation, but gradually, point by point, as orbital calculations refined themselves and the trajectory stopped looking like the messy, wandering path we normally associate with interstellar debris. I've studied orbital mechanics for decades, plotted countless hyperbolic visitors, modeled long-period comets, interpreted gravitational slingshots and stellar scattering events. And most of the time these objects behave like what they are: fragments hurled out by violent, chaotic processes, traces of planetary formation or destruction, leftovers that drift for eons through interstellar space, buffeted by random encounters, nudged by dust, plasma, stars, and molecular clouds. But 3I Atlas did not fit that pattern. Instead of skimming past our system like Oumuamua, instead of diving inward like 2I Borisov, it carved a path with shocking cleanliness, a smooth, calculated arc that did not simply pass through our solar neighborhood but targeted a very specific region, a point in space where the gravitational dominance shifts from the Sun to Jupiter. And to most people that may sound trivial, but to anyone who understands celestial mechanics, that distance is not accidental. It is a meaningful threshold, what astronomers call a sphere of influence boundary, a radius at which one gravitational regime yields to another. And the probability that a randomly ejected object, traveling for millions of years across interstellar space, undergoing countless perturbations, would arrive precisely at that boundary within a fraction of a percent is extraordinarily low. Not impossible, but statistically remarkable enough that it demands attention rather than dismissal. And yet, when I first pointed this out, the immediate response from many was to wave it away as coincidence. As if coincidence is a shield that protects us from having to confront uncomfortable implications. But in science, patterns are signals, precision is information, and ignoring statistically unlikely alignments simply because they complicate established narratives is the opposite of scientific curiosity. So I continued examining the data, refining the trajectory, checking for observational bias, atmospheric distortion, tracking errors, and still the precision remained. The object was not merely passing near Jupiter's orbit. It was heading directly toward the exact radius where Jupiter's gravitational influence begins to dominate the local region of space. Not closer, not farther, but right on the line, a location that matters profoundly for dynamical interactions. Because Jupiter is not just another planet, it is the gravitational gatekeeper of our system, the architect of orbital stability, the body that captures, redirects, or ejects comets, shaping the evolution of planetary orbits over billions of years. In every planetary system we've observed, the largest planet plays this role, dictating the flow of material and the long-term stability of smaller worlds. So if an interstellar object were interested, whether naturally or otherwise, in studying a system's structure, sampling gravitational gradients, releasing material strategically, or altering its own long-term path, that gravitational boundary would be the most strategically valuable place to pass through. And yet, NASA's recent briefing confidently declared that 3I Atlas is simply a comet, as if placing a familiar label eliminates the anomalies. I have no issue with confidence based on full acknowledgement of data, but confidence that disregards inconvenient observations is not scientific humility. One image shown publicly during that briefing displayed a linear structure emerging from the object, oriented in the direction of motion rather than away from the Sun. And for anyone familiar with comet physics, that is profoundly unusual. Natural comet outgassing produces jets, driven by solar heating. Sublimation of surface ices generates thrust that pushes material away from the Sun, creating tails that always point roughly anti-solar due to radiation pressure and particle flow. But 3I Atlas exhibits a structure that seems oriented forward, aligned with its trajectory, behaving nothing like a typical sublimation jet. And while I am not claiming artificial propulsion, the presence of a forward-oriented beam-like feature suggests a mechanism known or unknown that deserves investigation. Perhaps it acts as a micrometer-scale clearing effect, pushing aside dust and particles in its path, reducing the risk of collisions during high-velocity travel through dense regions. And whether such a process is mechanical, magnetic, electrostatic, or purely coincidental, remains unknown. But dismissing it because it challenges assumptions undermines the scientific method, which thrives on confronting anomalies, not burying them. And this is where the conversation becomes truly compelling, because many people ask the same oversimplified question. If 3I Atlas were meaningful, if it had purpose, wouldn't it head toward Earth, the planet? We inhabit the supposed center of importance, but that perspective reflects anthropocentric bias. Earth is not the gravitational centerpiece of the solar system. Jupiter is Jupiter sculpts, trajectories, captures, comets, ejects debris, shapes, orbital resonances, influences, asteroid belts, and governs long-term orbital architecture. Any process natural or otherwise interacting with gravitational dynamics would benefit more from encountering Jupiter's sphere of influence than approaching a small terrestrial world. Furthermore, an object passing through that region could release fragments that Jupiter's gravity would distribute across stable orbits, could subtly alter its own path using gravitational assists, or could use the interaction to transition into a long-term orbit around the Sun or be slingshotted toward another destination. The physics alone make this location strategically significant. Regardless of intent, and intent is not what I am claiming. I am claiming that physics has placed this object at a rare and meaningful intersection of forces, and that rarity merits investigation, not dismissal. Consider the difficulty of maintaining such a trajectory over interstellar timescales. For 3I Atlas to arrive on the precise angle and velocity required to hit this narrow gravitational window, it would need to avoid major perturbations from nearby stars, dense molecular regions, gas clouds, and interstellar dust. Any significant encounter could have shifted its course, altered momentum, or scattered it entirely. The fact that it still arrived exactly at this transition radius suggests either extraordinarily stable initial ejection conditions or some form of course correction over time. And rather than rejecting that possibility outright, we should ask what mechanisms might allow an object to maintain such precision naturally. Could it have originated from a stable, low-perturbation ejection environment? Could internal mass distribution create passive stabilization? Could outgassing in deep space create subtle but cumulative trajectory corrections? These are testable hypotheses. Yet instead of exploring them, the dominant response has been to reassure the public that everything fits within familiar categories. And reassurance is not science. Inquiry is. Exploration is. Willingness to confront the unknown is. And this is why I argue that 3I Atlas represents an extraordinary opportunity to study interstellar material, orbital dynamics, and gravitational interactions at a scale we rarely observe directly. If the object fragments near Jupiter's influence zone, we may witness natural distribution processes that mirror the formation of cometary families. If it alters trajectory, we may detect previously unknown mechanisms of propulsion or stabilization. If it releases dust or complex molecules, we may gain insights into chemical diversity beyond our system. Every outcome, natural or unexpected, holds value, but only if we look without prematurely closing the case. Science progresses when improbable events are examined with rigor, not when they are forced into comfortable narratives. And so as 3I Atlas approaches that critical region, we should watch carefully, measure precisely, and remain open to the possibility that the universe still has structures, patterns, and behaviors that challenge our assumptions. Because precision in the cosmos is rarely meaningless. And whenever an object from another star system demonstrates that level of precision, their responsible response is curiosity, not dismissal, humility, not certainty, inquiry, not complacency. The cosmos does not owe us easy explanations, and our role as observers is not to insist on simplicity but to embrace complexity when it appears, especially when it crosses our sky, carrying the momentum of countless years and the potential to reshape our understanding of how objects move between the stars. When an object traveling through the vast emptiness between stars suddenly behaves in a way that contradicts our models, even subtly, that alone warrants scientific attention. Because space is not forgiving, it does not easily allow precision. And yet after 3I Atlas passed perihelion, astronomers around the world began detecting something unusual, a faint but measurable non-gravitational acceleration, a deviation that could not be fully explained by simple gravity. And this instantly echoed the debate that erupted years ago with Oumuamua, the first confirmed interstellar visitor we observed, which also exhibited a similar unexplained acceleration, leading some researchers, including myself, to propose that sunlight pressure might have influenced its motion, possibly interacting with an unusually thin, sail-like geometry, a structure that could experience tiny but cumulative forces from photons pushing against it. And while that idea remained controversial, it demonstrated that our understanding of interstellar objects was far from complete. Now, with 3I Atlas, the observed deviation is smaller, subtler, but its significance lies not in its magnitude but in its direction, because the acceleration appears to be oriented in precisely the direction required to guide the object toward Jupiter's sphere of influence. Not approximately, not vaguely trending that way, but aligned in a manner that improves the probability of it reaching that gravitational boundary with remarkable accuracy. And this is where the anomaly deepens. Because if the deviation were caused by random outgassing, the chaotic venting of gas from heated surface ice, the resulting thrusts would be irregular, producing pushes in unpredictable directions, changing over time as the surface rotates, cracks, or erodes, random behavior that tends to scatter trajectories rather than refine them. making precision steering statistically unlikely, yet what we observe suggests the opposite, a reinforcement of the trajectory that places 3I Atlas exactly where it needs to be to intersect Jupiter's dominant region of gravitational control, and that raises a profound question about its internal structure and behavior. Perhaps the object contains layered materials that heat unevenly, producing directed mass loss, or perhaps internal cavities function as natural pressure chambers, releasing gas in a more focused manner, still natural but highly unusual. Or maybe its shape channels outgassing through specific vents, like a chimney effect that naturally creates thrust in one direction. And while such possibilities remain speculative, they are within the realm of natural physics. Yet we cannot ignore a third possibility, that some engineered or passive mechanism might be influencing its trajectory, whether a sail-like surface, an aerodynamic shape optimized for radiation pressure, or some internal system capable of subtle stabilization, and I am not asserting this explanation. I am not claiming artificial origin or deliberate steering, but I am saying that science must keep all possibilities open until the data eliminate them, because we do not get to choose which explanation feels comfortable. We only get to choose whether we follow the evidence wherever it leads, and the evidence in this case urges caution, curiosity, and humility, qualities that are essential when dealing with phenomena that challenge existing frameworks. We often forget how young our species is in cosmic terms. Humanity has existed for only a fleeting instant compared to the age of the universe. A cosmic blink in which stars have formed, burned, and died, planets have coalesced and been destroyed. Entire civilizations, if they ever arose, may have emerged and vanished before Earth even cooled enough to support life, and yet 3I Atlas, whatever its origin, began its journey billions of years ago, long before humans existed, long before mammals evolved, even before dinosaurs walked the Earth. Meaning that when we talk about its trajectory, its timing, its mass, we are not discussing a modern encounter between civilizations or technologies. We are discussing dynamics written into the deep fabric of cosmic time, shaped by forces and events that occurred ages before our species took its first steps. And that perspective should humble us, because the universe does not revolve around our timeline, our expectations, or our interpretations. The cosmos moves according to laws and processes far older than we are. And sometimes those processes produce results that appear intentional even when they are not. Precision can emerge naturally, but precision should always make us look closer. What matters most here is that we are finally reaching a point where we can treat such interstellar encounters not as isolated curiosities, but as scientific opportunities to expand our understanding of how material moves between stars, how gravitational systems interact, how objects preserve or alter trajectories across unimaginable distances, and how subtle forces perform cumulative work over millions of years, something our instruments could not have measured in previous generations. Today, we have global networks that coordinate observations, telescopes capable of detecting faint anomalies, spacecraft and sensors that can refine orbital models in real time, theoretical frameworks willing to revise old assumptions, and if we choose to exercise it, the humility required to accept that nature still holds surprises, that the universe is not obligated to behave according to our predictions. The fact that 3I Atlas is moving toward Jupiter's sphere of influence with such precision is not something we should dismiss lightly. Jupiter is not merely a large planet, it acts as a gravitational lens, a sculptor of orbits, a gatekeeper controlling the flow of comets and asteroids, shaping the architecture of the solar system, capturing some objects, redirecting others, ejecting many entirely, and for an interstellar object entering that region can have profound consequences. Gravitational interactions there can fragment material distributed across stable or semi-stable orbits, modify long-term trajectories, or even insert objects into bound solar orbits, meaning that if 3I Atlas releases fragments near this boundary, Jupiter's influence could spread those pieces into orbits where they remain accessible for study, or where they interact with other bodies, depositing material that originated beyond our system, potentially giving us chemical clues about distant planetary formation environments. This is why anomalies matter, why precision matters, because each unexpected behavior provides insight into processes we do not fully understand. And yet many dismiss anomalies simply because they create discomfort, because they challenge established explanations, because they require us to reconsider assumptions that felt safe. But science does not advance by ignoring outliers. It advances by investigating them, by asking why they occur, by constructing new models when old ones break. And right now, we are witnessing what may become the foundation of a new scientific discipline, what some have begun calling interstellar archaeology, the study of material that originated around other stars, carrying within it the chemical, physical, and historical record of environments we may never visit. Just as terrestrial archaeology begins with anomalies, a shard of pottery, an unusual structure buried in sediment, this field begins with objects that do not behave the way we expect. Objects like 3I Atlas, whose forward-oriented beam-like features, trajectory deviations, and gravitational precision suggest that there is more happening than simple cometary behavior. So why does it matter that 3I Atlas is heading so precisely toward Jupiter? Why should we treat this trajectory with seriousness rather than shrug it off as coincidence? The answer is simple but profound, because precision is a message, even when unintentional, a signal that natural processes can produce remarkable outcomes. Because anomalies are opportunities, not inconveniences. They reveal where our understanding is incomplete. Because science must value uncomfortable data points most of all. The ones that resist easy categorization. The ones that force us to ask better questions. And because in a galaxy billions of years old and unimaginably vast, an object that began its journey before our species existed may still carry information worth studying. Information about the worlds that formed it, the forces that shaped it, perhaps even the civilizations that might have arisen around its parent star. And though we cannot yet know the full story, we can learn from what passes before us if we pay attention. For now, the most responsible response is to watch, to measure, to compare models against reality, to gather as much data as possible while the opportunity remains, and above all, to remain humble, to acknowledge that the universe is always ahead of us, always more complex than the frameworks we build to understand it, and that every interstellar visitor may represent a step toward deeper knowledge. The next object may pass nearer, the next may show clearer features, the next may carry evidence we cannot deny. But we will only recognize such evidence if we train ourselves now to take anomalies seriously, to let precision guide inquiry rather than fear, and to treat the cosmos not as a solved puzzle but as an ongoing mystery that invites exploration rather than complacency.